Hello viewers, in today's module we will study the properties of ordinary least squares estimates part 2, sampling distribution. As earlier we are considering a 3 variable model where there are 2 slopes beta 2 and beta 3 which are estimated as beta 2 hat and beta 3 hat and compactly written as beta hat, a vector of order 2 cross 1. From our earlier modules we know that beta 2 hat is given as summation yi x 2I x 3I square minus summation yi x 3I summation x 2 x 3 all upon delta, where delta is summation x 2I square summation x 3I square minus summation x 2I x 3I whole square. You would have noticed already that this expression is linear in y, and because it is linear in y, once we substitute y as a function of ui, beta 2 hat becomes linear in ui as well. Substituting the value of y gives us beta 2 hat equal to beta 2 plus an expression which is linear in ui. So, beta 2 hat is linear in ui's. That, viewers, gives rise to an interesting property. We already know that the classical assumptions imply that each random disturbance term ui is independently normally distributed with mean 0 and variance sigma square, which means that beta 2 hat and beta 3 hat jointly follow a bivariate normal distribution with respective means beta 2 and beta 3. And the variance covariance matrix with which we are already familiar is given by sigma square small x prime x inverse, where small x is the deviation form of the two explanatory variables x 2 and x 3, that matrix being of order n cross 2. Specifically, beta 2 hat follows a normal distribution with mean beta 2 and variance sigma square divided by not just x 2I square summation, but this is pure x 2I square. In a few minutes we will take an intuitive look at these results and generalize these results to the k variable model. So, viewers, let us now explain the variance covariance matrix of the estimated vector b hat. So, we know that b hat is equal to beta 2 hat and beta 3 hat, and we had already explained that variance of b hat is equal to sigma square small x prime x inverse. What we must keep in mind is this matrix is called the variance covariance matrix. So, this in general terms has 4 elements: variance of beta 2 hat, covariance of between beta 2 hat and beta 3 hat, again covariance between beta 2 hat, beta 3 hat, and finally variance of beta 3 hat. So, that is the variance covariance matrix, and we know that expectation of beta hat is equal to beta 2 beta 3. So, therefore, beta hat follows a normal with mean b, b hat follows a normal with mean b, which is beta 2 beta 3, and variance covariance given by this matrix. We will take up each term at a time, and then we will go to the generalized version. Let us look at variance of beta 2 hat first. Here again, first we will take an intuitive route. So, we know that in the simple linear regression model where y is just regressed on single variable x, we should be able to recall for y equal to alpha plus beta x plus u, that is the two variable model, we have the result beta 2 hat. This is different from this beta 2 hat because this belongs to the three variable model. This is analogically we are trying to go to this result using the two variable model. So, this beta 2 hat follows a normal with mean beta and the variance was sigma square divided by xi square. That is the result we should be able to recall. We will see how the variance of beta 2 hat in the three variable model is going to be a modification of this expression for variance. In the two variable model, what is the format? Sigma square divided by summation xi square. Correspondingly, here we will have variance of beta 2 hat in the three variable model given as sigma square divided by summation x 2I square, because beta 2 is associated with x 2. In the single variable model or single explanatory variable model, we had only one x. So, this is just x, but in the three variable model we have beta 2 and beta 3, that is x 2 and x 3. So, beta 2 is associated with x 2I, but we need to put in another term here 1 minus r square 2 3. Let us explain what this term is. We can say that this is sort of summation pure x 2I square. Now, what is this purity about? The model is yi is equal to beta 1 plus beta 2 x 2I plus beta 3 x 3I plus ui. That is the three variable model where you do not have only x 2, you also have x 3. So, pure x 2I square is x 2I square cleansed or purified of the effects of x 3I. So, it is small x 2I square cleansed, purified of the effect of x 3I, small x 3I, and the association between x 2 and x 3 is given by correlation between x 2 and x 3. Association between x 2 and x 3, association between x 2 and x 3 is given by the correlation between x 2 and x 3. So, 1 minus square of that correlation means we have purged or cleansed x 2 of the effects of x 3. That means we have removed the effect of x 3 from x 2. In a similar manner, it will be easy to see that variance of beta 3 hat will be equal to sigma square divided by not just x 3I square, but cleansed purified effect, because x 3 also depends on x 2. So, that is sigma square divided by not just x 3I square, but x 3I square times 1 minus r square 2 3. So, if we collect these two information, now we can say that beta 2 hat follows a normal distribution with mean beta, and in the three variable model we have normal distribution with mean beta and variance given by sigma square summation x 2I square into 1 minus r square 2 3. So, that is the result for the three variable model. Similarly, viewers, beta 3 hat, if instead of 2 we write beta 3, what would we get? Beta 3 hat would follow a normal. Instead of beta 2, we would write beta 3 hat here, beta 3 here, and instead of x 2I, we would write x 3I. So, that is the intuitive explanation of the variance. Covariances will come in an easier manner when we go to the matrix formulation, which is what we will now take up. So, let us now take a look at the matrix formulation which arises out of the 3 variable model. Once we take a look at that, it will be easier to follow the k variable model. So, in the 3 variable model, we have b hat is equal to beta 2 hat, beta 3 hat, which is equal to x prime x inverse x prime y, which is also equal to x prime x inverse, that y is in deviation form. So, now we write x b plus u, and that boils down to x prime x inverse x prime x b plus x prime x inverse x prime u, which gives us b plus x prime x inverse x prime u. So, that is the relation between the estimate b hat and b and the disturbance terms ui's. So, therefore, by definition, viewers, variance of b hat is given as the expectation of b hat minus expectation b hat, and the transpose of this, the transpose is b hat minus expectation b hat with that transpose sign, which is equal to, if you look carefully, b hat minus expectation b hat means b hat minus b. So, the difference is x prime x inverse x prime u. So, that is expectation of x prime x inverse x prime u. That is the first term. The second term is simply the transpose of the first term. That means it is u prime x and then x prime x inverse. So, therefore, variance of b hat boils down to expectation of x prime x inverse and x prime u prime x, x prime u prime x, and then x prime x inverse, but all of these are non-stochastic, all of the x's are non-stochastic, only u is a stochastic variable. It is only the u vector which is stochastic variable. So, for all practical purposes, what we can do is we take out the expectations operator from here and we apply it just in front of the stochastic variables, keeping x prime as it is, and that we know is sigma square I. The reason is u prime is u1 u2 through un, and the transpose u1 u2 through un, which is basically equal to u1 square u1 times u2 u1 times un. Similarly, u2 u1 u2 square times u2 un and goes up to un u1 un u2 finally un square. Dear viewers, now just put the expectation operator in front. So, we will have expectation u prime is equal to expectation of this product, which is equal to expectation of this, and recall the classical assumptions. Expectation of each ui square is equal to sigma square homoscedasticity, and covariance between ui uj I not equal to j is 0. So, this matrix tells us that all the diagonal elements will be sigma square and all the off diagonal elements will be 0. So, off diagonal elements are all zeros. So, basically what we get is sigma square is out of the brackets common and we have an identity matrix. Let us put this result over here. Then what do we get? Sigma square x prime x inverse, that is the term in the middle. Then we have x prime x again. Finally, again we have x prime x inverse. So, that gives us a nice result, because the first two terms, they give us the identity matrix. So, we have sigma square x prime x inverse. Therefore, the result that we get is variance of beta hat is sigma square x prime x inverse. Here we have two explanatory variables x2 and x3. So, the order of this will be 2 cross 2. In fact, this whole thing is in matrix form, a 2 by 2 matrix. The first term is variance of beta 2, second term is variance of beta 3, rather variance of beta 2 hat and variance of beta 3 hat, covariance between beta 2 beta 3 hat and covariance between beta 2 beta 3 hat. In the next part of this module, what we will look at is how to expand this x prime x inverse and how to arrive at the exact expressions for variance and covariance. We have already given an intuitive explanation of this term. Now, we will look at the rigorous derivation of this term. So, viewers, now we will take a look at the matrix formulation of the 3 variable model. The model has 3 parameters beta 1, beta 2 and beta 3, which we write as beta, and we also write it as beta 1 and b, where beta 2 and beta 3 are written as a vector b. Similarly, for the estimates, we have beta hat is equal to beta 1 hat, beta 2 hat and beta 3 hat, which is also written as beta 1 hat and b hat. So, that is the way we denote the estimates and the original parameters. What we will do is we will focus on this as we have done, that is, we will focus on beta 2 hat and beta 3 hat. We will try to find out the sampling distributions of beta 2 hat and beta 3 hat. Now, we already know that variance of b hat, that is variance of beta 2 hat, beta 3 hat, we have already seen that this is equal to sigma square small x prime x inverse. We recall that x prime is equal to x2 prime and x3 prime, and x is equal to x2 and x3. So, x prime x by simple multiplication of 2 by 2 matrices will be x2 prime x2, x2 prime x3, x3 prime x2 and x3 prime x3. So, x prime x will be x2 prime x2, x2 prime x3, x3 prime x2, which is basically the same as x2 prime x3, and x3 prime x3, but that is equal to summation x2I square, because x2 prime is the entire row of observations on x2 and this is the same thing in column form. So, it is x2I square. What is x2 prime x3? Observations on x2 multiplied by the corresponding observations on x3. So, it is a product now, that is summation x2I x3I. and the reverse is also true. That is, if you take the transpose of this, because it is a scalar, the transpose is also the same. So, therefore, it is x 2I x 3I again, and finally, we have x 3I square. What we need to evaluate is x prime x inverse. So, let us put the inverse sign, and we know by the properties of matrix algebra that this will be equal to 1 upon delta or familiar delta, that is the determinant of this, x 2I square times x 3I square minus x 2I x 3I whole square, that is delta. And the remaining matrix is x 3I square on the top left and x 2I square on the bottom right, and towards the northeast corner we will have minus of x 2I x 3I, same on the left hand corner, that is on the southwest corner. So, that is going to be the expression for x prime x inverse, 1 upon delta times this matrix, where what is delta? Delta is equal to the determinant of this matrix, that is x 2I square x 3I square minus summation x 2I x 3I whole square. And as already explained, we will have basically a 2 by 2 matrix. The result will be a 2 by 2 matrix. This whole thing will be given by a 2 by 2 matrix. The first term will be the variance of beta 2 hat. So, what is the variance of beta 2 hat? X 3I square divided by delta, x 3I square divided by delta. The first term is the variance. So, variance of B hat is given by this matrix which has 4 elements. What is the first element? Sigma square into summation x 3I square divided by delta, but that we will find in a moment will come out to be exactly the expression that we have seen earlier. So, variance of beta 2 hat will be equal to sigma square and this first top left corner element, which is summation x 3I square divided by this delta, which is this expression, comes to x 2I square x 3I square minus summation x 2I x 3I whole square. It is easy to see that this x 3I term and this x 3I term gets cancelled, and if you divide by x 3I square, you get this result. So, you divide the numerator and the denominator by summation x 3I square, then you take summation x 2I square common. So, that will give us sigma square divided by summation x 2I square into 1, take out x 2I square, you get 1 minus x 2I x 3I square divided by x 2I square and x 3I square. And all viewers will immediately recognize that this term is nothing but r square 2 3. So, as we have already seen, variance of beta 2 hat will be sigma square divided by, if you recall the terminology, this is pure x 2I square. X 2I square cleansed of the effect of x 3 on x 2. Let us take a look at the bottom right hand corner. that is x2i square. So, x2i square divided by delta. Once again this x2i square will get cancelled. So, we can write variance of beta 3 hat will be as follows. Variance of beta 3 hat will be this term divided by this all into sigma square. So, that is sigma square summation x 2i square divided by delta, which is x 2i square x 3i square minus summation x 2i x 3i whole square. Cancel out the x 2i terms, that means you divide here by x 2i square, which basically is equal to summation x 3i square in the denominator 1 minus again that is equal to r square 2 3. Take out x 3i square, it comes in the denominator here. So, 1 minus this term, that will be summation x 2i x 3i whole square divide x 2i square x 3i square. So, we have taken a look at variance of beta 3 hat and variance of beta 2 hat. Let us write this in matrix form now. We have variance of beta 2 hat and beta 3 hat in a vector form is equal to sigma square, write a big matrix here. So, that is summation x 3i square summation x 2i square minus of x 2i x 3i minus of x 2i x 3i, this whole thing divided by delta, which is summation x 2i square summation x 3i square minus summation x 2i x 3i whole square. That is the final form. This term into sigma square divided by delta is variance. This into sigma square divided by delta is covariance between beta 2 hat beta 3 hat. Similarly, this one, and finally, this term into sigma square divided by this will be the variance of beta 3 hat. And therefore, we write that beta 2 hat follows a normal with mean beta 2 and variance sigma square divided by x 2i square 1 minus r square 2 3. Similarly, beta 3 hat follows a normal with mean beta 3 and variance sigma square divide pure x 3i square, that is a very useful term, pure x 2i square x 3i square. And you also have terms for the covariance. Covariance will be minus x 2 x 3i into sigma square divide by this. Now, finally, if we take a look at the k variable model, then these results generalize very easily. So, for the k variable model, if we go by the deviation form, then it will be b for the k variable model. For the k variable model, now b will be beta 2, beta 3 up to beta k, and beta will be beta 1 and b. So, if we are interested only in the slopes, then it is just b, and the results that we have are beta hat is equal to beta plus x prime x inverse x prime u. Similarly, b hat is equal to b plus small x prime x inverse small x prime u. So, we can use either of these two depending on whether we are interested in the entire range of the betas or just in the slopes. Oftentimes, we are interested more in the slopes than the intercept. So, let us take this example. As we have already seen, beta hat follows a normal with mean b, and we have already seen that the variance of this is sigma square x prime x inverse, where this x prime x inverse or x prime x will now be summation x2i square, x2i, x3i and up to x2i, xki. Again xk2i, x3i, x3i square up to x3i, xki, and write down up to xki, x2i, xki, x3i and finally up to xki square. So, that is going to be x prime x, and the inverse of this, put an inverse sign, put sigma square, that basically gives us the variance covariance matrix of this vector beta hat. This is not possible to do on the board or on the exercise books. We have a lot of computer software which work out these. What we had done was basically a 2 variable model. And finally, to end the discussion, if we focus now on the variable including the on the beta parameters including the intercept, then we have beta hat will follow a normal with mean beta, sigma square and capital X prime x inverse. So, that will add one more row and one more column.